Linear systems are challenging to solve because in general they are coupled. So in a simple example of a 2x2 system, you can see that a coupled system has both x's and y's appearing in each equation, and that makes it involved. Now, by contrast, the easiest systems to solve are decoupled systems, which means that in the x equation, there are only terms containing x, and in the y equation, there are only terms containing y. Each of these things can be solved by integrating factors. So, if we had a decoupled system, homogeneous or not, we could solve it very easily. And that means we lead ourselves to what I think is a natural question. Can we convert a coupled system into a decoupled system? And the answer is yes, you can. Not all the time, but you have to have a special kind of matrix. If your matrix A is non-defective, meaning it has a full set of eigenvectors. So if your matrix is non-defective, you can use what's called diagonalization. And diagonalization is what's going to allow us to write this system in decoupled form. So from linear algebra, you may or may not remember that if your matrix n by n has n eigenvectors, so if it has a basis of eigenvectors, then you can write a matrix factorization. You can write your matrix kind of like this: P, D, P inverse, where P and D are the following. D is a diagonal matrix that holds all of your eigenvalues along the diagonal and zeros everywhere else. And P is this matrix that has the eigenvectors that correspond to each eigenvalue in the proper spots. If you can do this, then you will be able to diagonalize your system and you will be able to decouple it. This will decouple the system. And why does it do that? Because remember, when you've got an eigenvector, all you do is essentially turn the action of the matrix into stretching. And you've essentially turned the problem on its side so that you're looking at it the right way, so that everything is effectively a stretch in one direction. You are picking the right directions to make this problem an easy problem. Okay, well, how do we do this? We are going to take our linear system, and it has this form. And if our matrix can be diagonalized, we should be able to write it like this: P, D, P inverse times X plus F. So what we're going to do is multiply both sides of this system by P inverse, and we'll multiply it on the left. And that's going to turn this into the identity. So we'll end up getting P inverse X prime is D P inverse X plus P inverse F. And we're going to make a substitution. We'll let Z, this vector Z, be P inverse X. So that means that Z prime is just going to be P inverse X prime. Now remember, this P matrix is a matrix of eigenvectors, so it's a constant. So our new system will be Z prime is equal to dz, so it's a diagonal matrix, plus P inverse F. So this is the new diagonal system. So the process is going to look like this. We are going to diagonalize, and we are now going to solve this system for z. And once we get the z, we have to solve this equation, z equals p inverse x. We have to solve it for x. So we would just go p times z. And it's a system that might seem complicated, it might seem challenging, but sometimes it'll save you grief compared to undetermined coefficients. Remember that undetermined coefficients is very straightforward, but it involves a lot of grinding, a lot of work, especially if you have a situation where your driving function is in your fundamental set. And in the last video, I showed you exactly that. So I'm going to go back to that example and hopefully try to convince you that with diagonalization, it's a little bit more straightforward. The solution here is always going to be the sum of the homogeneous and the particular. Now, we've already determined that the homogeneous solution is the following. It's C1, 1, 1, e to the minus t, C2, 1, negative 1, e to the minus 3t. So this means that the matrix A can be diagonalized. It has a full set of eigenvectors here. So we could write it PD, P inverse. The diagonal matrix is the matrix that stores the eigenvalues. It doesn't matter what order you put them in. They just have to live on the diagonal. And P then has to store those vectors in the correct order. So the vector that corresponds to the eigenvalue of negative 1 is the vector 1, 1. And similarly, this vector has to be 1, negative 1. Now, it's really easy to compute the determinant or the inverse of a 2 by 2 matrix. You essentially just swap the diagonal entries, change the sign on the off diagonal entries, and then multiply by the determinant, 1 over the determinant out front. So you may need to remind yourself about this formula, but the determinant or the inverse of a 2 by 2 matrix is pretty straightforward to find. 1, 1, 1, and a negative 1 if we absorb that negative sign from the front. Alternatively, you could just sit there and compute the actual inverse by row reduction. You'll get to the same place no matter what. So this takes care of our homogeneous problem, and now what we're going to do is go ahead and attack the diagonalization. So we are going to use this diagonalization idea. If we want, we could start again from the whole beginning just so we remind ourselves of the procedure. PD, P inverse x plus f. We are going to take advantage of the fact that that matrix is diagonalizable. We're going to hit everything on the left with P inverse. And that means we're going to make a new substitution here. We'll have that z prime vector is dz plus P inverse f. So we need to construct this new system. Now note, P inverse f is us having to do a little bit of matrix multiplication. The right-hand side vector is 6 and 0 with an e to the minus t. So we'll get e to the minus t over 2. We'll get a 6 up top in this entry and another 6 there. So this is going to give us 3 halves e to the minus t, 1, 1. So this is what ends up living, or sorry, not 3 halves, just a 3. This is the new right-hand side of our diagonalized system. So that means z prime equals dz plus P inverse f gives us the following. We're going to get z1 prime, z2 prime is equal to negative 1, 0, 0, negative 3, z1, z2, plus this guy right here. So we get 2 decoupled first-order linear DEs. we can solve this. Z1 prime is negative Z1 plus 3e to the minus t. Z2 prime is negative 3Z2 plus 3e to the minus t. So let's call that equation 1, that equation 2. We can solve these very straightforwardly, and it's easiest to do this with an integrating factor. So the integrating factor in this particular problem, remember the coefficient here is 1, so the integrating factor is going to be e to the dt, so we'll get an e to the t. This very conveniently, if we multiply both sides here by the integrating factor, that term will go away. We'll have d by dt, z1 e to the t is 3. So z1 e to the t will be 3t plus an arbitrary constant that we'll call c1. And that means that z1 will now be 3t e to the minus t plus c1 e to the minus t. So that's going to give us z1. That's the advantage of diagonalization. We've turned our system from a coupled system to a decoupled system. We have diagonalized it. We've turned our head just the right way so that the two equations are solvable by standard methods. The second equation we want to solve, z2 prime plus 3z2 is 3e to the minus t again, just from above there. The integrating factor will be e to the 3t in this particular case. And when we go ahead and we solve this, we'll have that the derivative here will be z2 e to the 3t is going to be 3e to the 2t. So if we multiply both sides by the integrating factor, it's going to turn into the following there. And integrating this, we'll find that z2 e to the 3t is going to give us a 3 halves e to the 2t plus c2. And that means that z2 will be 3 halves e to the minus t plus c2 e to the minus 3t. So what we now need to do is go ahead and determine what the original variable is. So now what we need is x. Remember, we made this definition that z was equal to p times x, or sorry, p inverse x. So that means that x is simply going to be found by us multiplying p times z. That means we take the original matrix of eigenvectors, 1, 1, 1, negative 1, and we now take a vector that holds each of these two solutions. So we'll have 3t e to the minus t plus c1 e to the minus t. And we'll have 3 halves e to the minus t plus c2 e to the minus 3t. If we go ahead and do a matrix vector product, what we're going to find is we'll have 3t e to the minus t. So everything in the top row, c1 e to the minus t, added to everything in the bottom row, c2 e to the minus 3t. And similarly, we'll have 3t e to the minus t plus c1 e to the minus t, subtract everything in the bottom row. So we have to do a little bit of algebra, a little bit of work to go ahead and organize these things. But once we do that, it should work out very straightforwardly. So we'll have 3t e to the minus t plus 3 halves e to the minus t. And what we can do then is try to group together all of these terms according to the power of t that they've got. So I'm going to go ahead and break this up into several vectors. So I'll have the following. 3t e to the minus t appears in both terms. I'll have a negative 3 halves e to the minus t on the bottom, but a positive on the top. I'll have a c1 e to the minus t 1, 1, and a c2 1, negative 1 e to the minus 3t. So no surprise, this is the homogeneous solution. So you can simply absorb this into that homogeneous solution. This ends up being the particular solution. So the particular solution here is 3. Let me write it in a similar form to what was given previously. 3 t e to the minus t. And now what we'll have is this 3 halves, negative 3 halves, e to the minus t. Now you might say to yourself, okay, we're done. But if you're paying attention, you might say, well, hold on, wait. Because in the previous problem, when we did this with undetermined coefficients, we found that the particular solution was 3, 0 e to the minus t and this 3, 3 t e to the minus t. They don't match. Why don't they match? Trickery. Trickery, my friends. When you've got this term, e to the minus t, you could interpret it as 3 halves plus 3 halves, 3 halves minus 3 halves. All of these times e to the minus t. Why on earth would I do that? Well, 3 halves, e to the minus t, 3 halves minus 3 halves, e to the minus t. This term right here, this term is simply part of the fundamental set, whereas the other one is not. This is in the fundamental set because this combination right here is exactly the first solution in the fundamental set. But this one is not in XH. So what we could have done is, you can see for yourself that taking this undetermined coefficients, we were a little bit lazy in the video in the prior, we just stopped. But what we should have done is broken this up and realized that, we can absorb part of it into the homogeneous, and the part that's left is not in the homogeneous because this vector is not the right eigenvector. So as before, the particular solution matches exactly what we got. So it's good to have an alternate way of doing things, and diagonalization provides you with an alternative.